just want it. Can you see myself? Can you see myself? Can you see myself?
By the light of an ancient campfire, a discovery was made that changed the course of history.
We don't know exactly how it happened, but I sometimes wonder whether it wasn't a complete accident.
Whether by chance or through sheer determination, once humankind learned how to harness the power of fire, we left the Stone Age behind, forging our way into the modern world with copper, bronze, iron, and steel, the metals.
A world without metals would not have tall buildings, it would not have fast vehicles, it wouldn't be able to have electricity. Really, our entire modern world is built on the backbone of metals.
Our journey begins with a metal that's transformed life on Earth through its beauty. A metal that fortune hunters were willing to die for. And not just in the movies.
There's nothing more beautiful than gold. Nothing in the world. You just feel it when you see it. Ancient people valued gold before the concept of currency or money even existed. It's something that people intrinsically knew had worth. Gold is absolutely magical. Gold is the most fantastic jewelry metal to work with. It's so soft, it's so flexible. It's like butter. Working with gold ruins you for any other metal. You're never the same again.
Jeanette, a master jeweler, is making a pair of gold earrings.
I specialize in ancient jewelry making techniques. The kind of expertise and skill that were used for making jewelry really made it an art form. I'd make my own wire and sheet and practice techniques like granulation. The technique I'm going to use for the hanging fringe actually originates from Troy from about 2450 BC.
Gold is unique among the elements. Gold is extremely resistant to oxidation, to rusting. If you make an object out of gold, it's the one thing that you have that doesn't degrade. So to ancient people, it must have been very, very appealing.
The color of gold draws you in. Ancient people saw it and knew that it was something incredibly special.
Gold is not only beautiful, it's rare. In fact, if you take all the gold that's been mined to date, it's estimated it would fill about a third of the Washington Monument. But to understand what makes this rare and noble metal last forever, we need to take a closer look. A much, much closer look. Using one of the most powerful electron microscopes in the world, David Mueller studies the elements.
Probably the most fun in the lab is when you put something in and the picture comes up and you look and you go, well, that's not what I expected. That's interesting, and that's usually the start of a new scientific discovery.
Today, Mueller is observing the curious behavior of gold, atom by atom. All elements are made of atoms. Inside is a nucleus filled with positively charged protons along with neutrons that have no charge at all. Swirling around the nucleus in a cloud are negatively charged electrons. It's the relationship between gold's nucleus and its electrons that holds the key to its resilience.
We're now at 7,000 times magnification, 7 times higher than the highest magnification of an optical microscope. And if we zoom up some more, we can start to see there's this nice pattern. These are little islands of gold. And if we zoom up a little bit further on them, you'll start to see little bright spots all by themselves. Those are individual atoms.
Every one of these clusters contains thousands of bright dots, thousands of gold atoms.
Little gold atoms form small clusters, and they keep rearranging and changing. They're not static, they're not stable, they're dynamic, they're moving all the time.
Gold atoms love to be together. But when it comes to bonding with other elements, they're downright antisocial. When atoms bond, they do it through their outermost electrons, by sharing or swapping them. But gold's 79 protons fight the urge. because they have an immense positive charge.
That positive charge pulls in the electrons. The real consequence is that the outermost electrons of gold are much less available for doing chemistry than we might otherwise expect.
That's why gold doesn't bond with elements like oxygen that cause metals to tarnish and rust.
The reason that we're able to appreciate the gold masterpieces from 2400 BC is because gold lasts forever. It is just as beautiful today as it was thousands of years ago. You can't say that about anything else that you could work in.
How did such a unique metal form?
It's not easy to make an element. You need temperatures that are extreme, and we're talking millions of degrees. The heavier the element, the hotter the temperatures required to make it. And you find those temperatures in the cores of stars that are 10 times the mass of the sun or greater.
It's within the intense heat and pressure of these massive cores that the elements progressively take shape, bonding together in a process called fusion.
You can sort of imagine building up all the elements that exist in the universe by taking a pile of neutrons and protons and electrons and putting them together to build up bigger and bigger and bigger atoms.
When the number of protons and electrons hit 26, forming iron, the process stops.
Once iron's made in the core, that's it. There's no more available energy for fusion. Those massive stars will explode and go what's called supernova.
One of the key open questions, though, was what about the heavier elements? What about gold and platinum and uranium? Where do those come from?
At the end of supernova explosions, new kinds of stars are formed, called neutron stars. They often come in pairs, binary stars.
They're extremely dense and compact and heavy. It weighs about 1.5 times the mass of our sun, but it's the size of a city like New York or London or Boston. And they incorporate a lot of neutrons, which is why they're called neutron stars.
Some scientists theorize that elements heavier than iron were created in the collision of two neutron stars. What happens when they collide? Fusion on a massive scale. The elements were spread throughout the cosmos, so they were in the mix when our solar system formed 4.5 billion years ago. And later, more were delivered to Earth by comets and asteroids. Most of the elements on the periodic table came to us from space. We classify them in groups defined by their characteristics. The largest group is the metals. And one of the most beautiful by far is gold. Now, this ancient treasure is going back to space. On board the most advanced telescope ever built.
It's the next big space telescope. We like to call it Hubble 2.0.
Hubble 2.0 is the James Webb Space Telescope.
2018, we're going to launch this incredible telescope, the largest space telescope mankind has ever built. And we're going to send it 1 million miles into space to stare at the earliest part of the universe. And it will all rely on 2 ounces of gold.
The ultra-thin layers of gold that coat the telescope's mirrors give it the power to detect galaxies light years away.
Hubble has sort of found the edge of the visible universe, but we know there's a whole universe beyond that at wavelengths called infrared wavelengths.
And that's where gold comes into the picture.
Infrared light is invisible to our eyes, but we can detect it as heat. And that's why this thermal infrared camera will pick it up. So this is my hand as viewed by the camera, and it's about 97 degrees Fahrenheit. Now, let's look at my hand reflected in this ordinary silver-coated mirror. It says that my hand is 84 degrees Fahrenheit, which is a lot less than 97. And that's because the silver-coated mirror is not a perfect reflector of infrared light. But if we try this gold-coated mirror, now when I pass my hand's reflection over the gold, it says that my hand is 97 degrees Fahrenheit. And so what this shows is that gold is an almost perfect reflector of infrared light. And that's why we coat all of the mirrors of the James Webb Space Telescope in gold, so that it has an almost perfect view of the infrared, invisible universe.
Gold is that ancient treasure that we've lusted over mankind's history. And here we are in the 21st century using this to actually unlock the secrets of the universe and perhaps the origins of where we came from. What a wonderful historical transformation.
Historically, this glittering treasure of the Earth could be found in riverbeds and streams. But in order to leave the Stone Age behind, we needed another metal, one strong enough to shape into tools. And we found it in the flames of a fire. Copper, atomic number 29. 29 electrons, 29 protons, and 35 neutrons, is embedded in a mineral called malachite.
Malachite has this incredible colour, doesn't it? It's like a Wizard of Oz Emerald City green. Malachite has been really important throughout the history of our civilization. This is probably the first mineral that humans used to actually extract copper metal.
Just imagine the following. Someone comes home with a beautiful green rock, malachite.
They decide to grind it into a powder and throw it into a campfire.
A magical process occurs.
Nature puts on a light show as the edges of the flames turn emerald green.
The flame suddenly becomes greenish. You get these incredible colors. You have no idea where they come from, but it certainly provides entertainment. And at the same time, that beautiful green rock slowly turns black.
The beautiful green malachite has burnt away. What's left behind is copper, combined with oxygen from the air, copper oxide.
If you left it in the fire overnight to burn, then the transformation would have gone even further.
But in order to free copper from oxygen requires another ingredient, carbon, which is conveniently provided by charcoal, the residue of burning wood.
I want to recreate that for you.
Sella drops a disc of copper oxide into a crucible of charcoal and heats it up in a modern-day fireplace, the microwave.
What heat really means is the molecules and atoms begin to move much, much faster. Now it's possible for the carbon to actually strip away the oxygen, disappearing off invisibly into the air as carbon dioxide. But the next morning, the person who's cleaning up the fireplace, almost certainly a woman, would have found tiny little shiny nodules lying amongst the ash. That would have been metal. This is a magical transformation that would suddenly have given you a material that you could shape, that you could reuse, that you could make tools with. This was power indeed. This was a birth of a whole new technology.
This was copper. Once our ancestors discovered how to free metal from stone, the art of smelting, they had a material they could shape into bowls and tools. But they also discovered it has another surprising quality. An ancient Egyptian medical text dating back to 1600 BC reveals copper was used as a disinfectant to clean wounds. It was also used to make surgical tools. As late as the 19th century, during a cholera epidemic in Paris, copper workers seemed to be immune to the disease. But by the 1940s, with the development of antibiotics, people lost interest in copper, its medicinal powers forgotten. Until now. At the University of Southampton, Bill Keevil has set out to prove copper can help solve a dangerous problem: hospital-borne infections.
If a jumbo jet full of people crashed each day and everyone died, would you fly? Probably not. That's how many people die in America each day from hospital-acquired infection.
Hospitals are a breeding ground for dangerous superbugs. Just about any surface you touch is a hot zone.
We know superbugs are perfectly happy to survive for many weeks on a dry touch surface such as stainless steel or plastics. So we need something that works 24 hours a day, 7 days a week.
Could copper be an answer? Keevil puts it to the test. He takes a piece of copper and a metal commonly used in hospitals, stainless steel, and coats them with the superbug MRSA, along with a green fluorescent dye. Next, they place it in a microscope.
Please start your clocks, and we will follow this experiment over the next 5 minutes.
At first, the bacteria on the copper and stainless steel glows bright green. But within minutes, the copper in the screen on the right turns black.
This is what they look like at the start of the experiment, and this is after 5 minutes. So you can see they're all dead.
How does copper do it? Scientists suspect it has something to do with the membrane of a superbug, which has an electrical charge. When it meets up with copper, a kind of short circuit occurs. The copper penetrates the membrane, leaving it with gaping, oozing holes. The copper invades the superbug, destroying its DNA.
If there's no DNA, there's no growth, and in fact, there's no chance of mutation, and therefore you can't get resistance.
Copper's ability to kill germs could one day save millions of lives. But it's already revolutionized the way we live, because copper has another extraordinary ability. It conducts the electricity that powers the planet.
Metals are extremely unusual materials. They can conduct electricity extremely well. And when we think about conducting electricity, what that means is that there are electrons within the material which are able to move.
Sometimes this is described as a sea of electrons. You can kind of picture these individual atom cores and then this sea of electrons all around them.
Metal atoms are arranged in orderly rows and columns. In between those columns are electrons that are able to move around.
When we apply a voltage with a battery, we can start to draw electrons so that they all move collectively in one direction.
With a voltage applied, electrons hop from one atom to the next.
That's what gives us the electric currents that are so useful.
While all metals can conduct electricity, copper is one of the best, and it's abundant. The worldwide supply is about 6 trillion pounds. But the qualities that make copper the metal of choice to wire the planet also limit its usefulness. That sea of electrons not only conducts electricity, it creates flexible bonds between the atoms.
The atom cores can move through this sea of electrons in a relatively easy way, and that's what makes metals malleable.
But a metal like copper, which is malleable enough to be stretched into thin, flexible cable, does not a dagger make.
Copper is actually too soft. A blade made of copper loses its edge within moments. And yet, by combining it with other rocks in the fireplace made of tin, you could make a material which was stronger, harder, and stiffer. That was bronze.
Around 2500 BC, humankind took the art of smelting one step further by mixing metals to create an alloy.
When you look at copper, it's pretty boring. Every single atom looks the same. But when you look at bronze, there are two different types of atoms. There's copper and there's tin.
Adding tin to copper changes the properties of the metal. The larger tin atoms restrict the movement of the copper atoms.
It makes it more difficult for the atoms to move past one another to change shape. Saying that it's more difficult to move them around is equivalent to saying that the metal is stronger.
Bronze would have provided useful implements for agriculture, but more importantly, it would have provided you with weapons to establish your dominance. And dominance, of course, means control. And control means power.
The movies paint a vivid picture of how bronze transformed the nature of warfare.
It's the Bronze Age, so without bronze you don't stand a chance in battle. Bronze is like no other material people would have handled before. With it you can make harder weapons, you can make sharper blades, and you can make them consistently. You can cast them in mold and make them always of equal quality. With bronze you can, for the first time really, equip hundreds, thousands of warriors with the same types of weapons, all of which will perform and be equally lethal. So it probably meant a revolution in warfare.
But not all swords are created equal. Back in 1965, a group of archaeologists discovered more than 50 ancient tombs in the Hubei province of China. During the excavation, they unearthed something extraordinary. Ti Gao Hu was one of the first people to lay eyes on it. Hu, an expert in the preservation of ancient relics, vividly remembers seeing a most unusual sword.
The sword had a golden sheen to it, and had a decent weight to it. It had the shine of fresh copper. There was no rust at all.
Although it had been buried for more than 2,400 years, the sword was perfectly preserved. Hu found 8 characters written in ancient Chinese script on the base of the blade. They identified the sword's owner, Go Tian, the king of Yue, a famous ruler in the 5th century BC.
Everyone came to see the sword, ecstatic because there were characters on it. One young man was particularly excited and he tried to reach for it and he bumped into me. I leaped forward a little and I must have touched the sword. And the sword made a cut about 2 to 3 centimeters on my hand. There were droplets of blood coming from my wound. It wasn't a deep cut, but the cut anyhow, like a shaving razor. The sword was that sharp. Later, they tested the sword. It could cut through 20 sheets of paper. It was so beautifully crafted. I was astounded. The Goujian sword is well preserved because of its burial condition. It is dry, and no water leaked inside, thus it did not rust.
But its longevity may also be due to the extraordinary craftsmanship with which it was made.
The smelting technology from ancient times has been lost. But recently, there are people who start to imitate the styles. However, they can't manage to replicate its sharpness. The sophistication cannot match up to ancient times.
But bronze has another resounding quality. It's the perfect metal to forge a bell. In South Korea, master craftsman Song Chang-il is making a 10-ton bell for a Buddhist temple. After decades of experience, combined with an artist's instincts, he knows exactly what it takes to make a bell with the perfect ring. First, 10 tons of copper and tin are heated to 1150 degrees Celsius. When the time is right, Chang-il pours his concoction into a massive clay mold. The metal is so hot, it takes 2.5 days for the bronze to cool. Finally, the mold is carefully removed. And the bell is tested for the first time.
That sound that we hear is really telling us about the stiffness and the resilience of the material. So when we hear the ringing sound of a bell, the entire material kind of swings. It becomes elastic and can then come back and go forward and back and forward and back.
Over thousands of years, through trial and error, craftsmen like Chang-il discovered that the perfect ring could only be achieved with the perfect recipe. A balance between tin and copper. But around 1200 BC, as the use of bronze spread, and with supplies of tin scarce, once again, the flames of a fire brought us a powerful metal. Iron. Atomic number 26. 26 electrons, 26 protons, and 30 neutrons. Freeing iron from stone meant taking the technology of smelting one giant step further. Charcoal burns at about 1,000 degrees Celsius, But to smelt iron, the flames need to be a lot hotter. The answer? A technology that could literally fan the flames. A furnace called a bloomery. This ancient furnace was built with heat-resistant walls made of earth, clay, or stone. At the base, pipes allowed air to enter through an elaborate system of bellows. The air was pumped manually, by hand or by foot.
Anyone who's been camping and has made a little campfire knows that if you lean down and you blow into the embers, what they do is they glow much more brightly because you're introducing oxygen and you're raising its concentration, you're making it more available.
A fire needs oxygen to burn, and the more oxygen, the hotter the flames.
The reaction of oxygen with the charcoal, which makes carbon dioxide, is one which generates an increase in temperature. You get a release of heat.
Oxygen made the fire hot enough to separate iron from stone. And once again, metal transformed the way we live, from tools to weapons. In time, the bloomery was replaced with the more powerful blast furnace. And by the 20th century, iron was everywhere. The Industrial Revolution changed nearly every aspect of life on Earth. But there was a catch. In the process of smelting iron, impurities called slag are left behind. Slag weakens metal. Over hundreds of years, craftsmen discovered that if iron is hammered and reheated over and over again, it gets purer and stronger.
Over time, bit by bit, they discovered how to get more and more of what they wanted in terms of properties. But they certainly didn't have any understanding at anything even remotely like the atomic level of what was going on.
But now we understand that at the atomic level, an extraordinary transformation was taking place. Iron was turning into one of the strongest alloys on Earth, steel. While hammering drove out the slag, the charcoal in the fire provided an essential ingredient, carbon.
The combination of iron and carbon to make steel is almost a unique combination in the world. And key to it is that the iron atom and the carbon atom are very different sizes. When you add a little bit of carbon to iron, it tends to hide in the little gaps in between the large iron atoms.
The way tin transforms copper into bronze, carbon turns iron into steel.
And this is one of the amazing things about steel. Just using more or less just these two elements, iron and carbon, you can create lots of different properties that can be useful for different applications.
To demonstrate the difference between iron and steel, Vinci got access to a piece of one of the most famous iron towers ever built.
This is our piece of the Eiffel Tower.
Discarded after a repair.
I never thought in my life I would be holding a piece of the Eiffel Tower. I mean, I've been up the Eiffel Tower a couple of times.
The Eiffel Tower is made of wrought iron, which has less carbon than steel.
When the Eiffel Tower was built, wrought iron construction was really at its peak. It's an amazing structure using an amazing material, especially for its day.
How does the strength of the wrought iron in the Eiffel Tower hold up against steel? Rick Vinci and Helen Chan are about to find out.
Not only do we get to hold a piece of the Eiffel Tower, but we also get to cut it up and bend it and maybe even break it.
They conduct a bend test to determine how much force can be applied to the wrought iron before it bends. It not only bends, it breaks.
Wow, it broke. Okay, this is actually cracked.
When they test the steel, there are similarities and differences.
Well, it actually seems as if the two samples behave pretty much the same. The load that it took to bend it was comparable.
Okay, so I see two differences right away. First of all, the wrought iron bar cracked and the modern steel didn't. But I see another really important difference, which is The modern steel bar is only half the thickness of the Eiffel Tower bar, despite the fact that it carried exactly the same load.
So what that means is if you're using a modern steel, for the same amount of material, you can support 4 times the load.
Wow, all right.
In fact, around the time the Eiffel Tower was built, steel was already on its way to becoming the metal of choice for building high. Chicago's towering 10-story home insurance building, the world's first skyscraper, had a steel frame.
Steel had a huge influence on the development of this country as an industrial nation.
And today, steel can do things that are hard to imagine. Nothing demonstrates that quite like the Beijing National Stadium, nicknamed the Bird's Nest. 42,000 tons packed into a design that seems to defy logic. Engineer Michael Kwok was a project manager for the design and construction of the Bird's Nest.
It's more like a jigsaw puzzle. You just try to figure out how this will put together. And this is exactly the cleverness about this building.
It is very unlike pretty much any other structure that's been built. If you want to make a strong structure, there are certain classic shapes that work very, very well, and the truss is a classic one. If you look at bridges all over the place, they have these triangular elements, these truss elements that are very, very strong.
The geometry of a triangle makes it an inherently stable shape. Put several of them in a row, and they distribute the weight of a structure to its load-bearing beams.
But Bird's Nest looks nothing like that.
But looks can be deceiving. 24 sets of columns connect to a series of trusses that support the roof. All this is hidden behind a maze of steel.
Can't make that out of just any run-of-the-mill steel. You need a particularly high-strength and tough steel.
The stadium is made of 2 kinds of steel. The recipe for the trusses provides extra strength.
We use special steel at the location where it's most stressed, where you take up the highest loading. If you look at this column, it is the bending parts which actually take up the heaviest loading. And this is where we use the thickest steel.
But to create the beauty of its winding exterior required steel with more flexibility. For a massive steel structure like this, the combination of flexibility and strength is critical, especially in an earthquake-prone region like Beijing.
Steel can stretch and elongate without breakage. This is what we need. We need elements to be able to deform without breaking. When an earthquake comes, the roof will move a lot, but actually it's okay. It moves means it dissipates energy. It doesn't actually affect its stability, and actually people underneath the roof can actually evacuate.
The bowl of the stadium, made primarily of concrete, does not have the elasticity of steel. So the engineers and architects came up with an innovative idea. Separate concrete from steel. Make them work as 2 independent structures.
So the 2 actually are completely separate. So when earthquake comes, the 2 actually will respond differently.
The extraordinary properties inherent in steel make it possible for engineers like Michael Kwok to build structures like this that capture the imagination.
People really love the Bird's Nest because it's not just a simple stadium. Probably more accurate way of describing it. It is sculpture made by steel.
Today, by mixing different types of steel for different purposes, engineers have taken the art of steelmaking to new heights, literally. The tallest bridge in the world, the Millau Viaduct in France, is made of steel that contains an element that's quite rare, niobium. It is a soft, whitish gray metal, and if you add it to steel, you get a stronger, lighter material.
When you think about a solid piece of metal, it just looks like it's all the same. But in fact, if you really zoom in, that chunk of metal is typically made up of lots of little individual metal grains. And it turns out that if you can make those grains really tiny, then it makes it much more difficult for the atoms to move past one another to change shape. So by making the grains tiny, you make the metal stronger. Now, niobium prevents the growth of these grains very effectively. And then you can get incredible strength that comes from having this very tiny grain size.
Different kinds of steel can have other additives like nickel, chromium, or manganese. But there's one rather bizarre recipe that could help solve one of the world's biggest problems.
We've been seeing landfills as a huge environmental burden. And of course, it appears that way on surface because we don't know what else to do with it. But if we can reform end-of-life materials into completely different products, then suddenly landfills shouldn't be seen as a burden. They should actually be seen as this amazing possibility. It's a treasure.
Veena Sajwala has developed a way to recycle the stuff nobody wants, trash, and turn it into steel.
The most basic steel is nothing but an alloy of iron and carbon. Well, guess what? We can find carbon in plastics.
The first step, take some plastic like this broken headlight,
So, Rufat, look at what I got you.
cut off a piece, and melt it down to a small pellet, chock full of carbon. Top it off with a lump of pure iron. Place the combo back in the furnace and heat it up. Now, watch the alchemy unfold as the carbon in plastic bonds with iron.
What's exciting here is that we're actually seeing this high temperature reaction taking place right in front of our very eyes. We've got this liquid metal. We're now looking at how this is interacting with this source of carbon, which of course is the plastic that came from a waste out of a car. Carbon from that plastic is actually able to dissolve into liquid metal. So this is what's come out of the furnace. We've dissolved the carbon from the plastic into liquid iron. And of course, what we have here is steel.
After a decade of research, Veena's green steel is slowly making its way out of the lab. Partnering with the manufacturer One Steel, they have already recycled over 2 million tires. Today's tires are made of a synthetic rubber, produced from oil rich in carbon, the perfect ingredient for green steel. And when it comes to greenhouse gases, Veena's steel requires less coal to cook, and that reduces its carbon footprint.
As the saying goes, one person's trash is somebody else's treasure. Guess what? This could become a society's treasure. I love steel because it has really given us the structures that have changed this world around us.
Steel has given us the power to build high and strong. But as wonderful and versatile as it is, steel has limitations.
One of the drawbacks to steel is that it is relatively heavy. Iron is fairly dense, and for its strength, you have to make massive structures. And that's fine if you're building a bridge, but it's not fine if you're building something that needs to move.
And that's where another extraordinary metal comes into the picture. Atomic number 13, aluminum, has just 13 electrons, 13 protons, and 14 neutrons. In comparison with a heavier metal like iron, which has twice the number of protons, electrons, and neutrons, the aluminum atom is incredibly light.
Aluminum has an ethereal lightness that no one could believe.
And yet, it also has some of the properties, like steel, that allow you to modify its strength and its other characteristics to optimize it.
Aluminum has completely transformed our world. From the trivial tent pegs of our tents to the frames of our aircraft, where it really makes a difference. If we had to build our airplanes out of steel, they would have to have fuel tanks 5 or 6 times bigger than they do now, and would carry a third of the passengers.
Today's aluminum is really fabulous stuff. If you can live with a little bit less strength in exchange for a lot less weight, then aluminum is an excellent choice. But as we look to the future, another way to move forward is to ask ourselves if what we have been doing with metals for all of these years is the only thing we can do.
Imagine a material that is not just light, not just strong, but flexible enough to change its shape.
So I think of the Terminator with this project, which is super fun. And I don't think I've seen the Terminator since I was young, but one of the images that really stuck with me is the T-1000, you know, the all-metal guy, right? He can change shape and then self-heals. Actually, our material does all those things.
This is metal foam, a combination of metal and rubber. Heat it up and it morphs into another shape. And when it's done, it becomes a solid again.
The idea of this metal foam is that we can have something that changes its shape dramatically, then after it changes its shape, have a lot of strength.
What's the recipe for making metal foam? First, take a dash of Himalayan salt. Add a little dragon skin, also known as uncured silicon. Mix it up. Pour the mixture into a mold and let it cure. Remove the concoction from the mold and place it in an ultrasonic cleaner. This dissolves away the Himalayan salt. What's left behind is a porous, sponge-like material riddled with tiny crevices. Next, submerge the foam into a bath of molten Fields metal.
Fields metal is a low melting temperature alloy of indium tin and bismuth. So at 60 degrees Celsius, it is a molten liquid. Below 60 degrees Celsius, it's a frozen solid.
The metal-covered foam is sealed in a vacuum chamber where the molten metal seeps into those tiny crevices that were left behind by the salt. Air trapped in the foam is pushed out and rises to the surface. The sample is then removed from the vacuum chamber and cooled down. Once it's at room temperature, it hardens again. Shepard hopes one day metal foam will be able to make like a bird.
One of the problems I'm trying to solve with this material is inspired by a puffin. A puffin can fly, but then it can dive underwater to catch fish. So it has to sweep its wings back in order to not have its wings torn off. So in an artificial version of the puffin, we would want a vehicle that could turn from a plane to an underwater glider. This idea is quite imaginative and a far-reaching goal, but we are currently working on a wing that we will coat in a skin of this metal foam, and we're going to try it out on a radio-controlled airplane in the next year.
But metal foam could find another home in space.
If you think about kind of a limited resources setup, certainly if you're like in outer space and you have a limited number of things you can bring with you and maybe you don't know exactly what tools you need, but here you have this material and you can really change its shape and then lock it into whatever you need. So you can take it one day and use it as a wrench and take it the next day and use it as a hammer.
One day, metal foam could make its way into your toolbox.
Eventually, we believe this composite could be used for reconfigurable tools. At this point, we think there are some flaws in the structure that may cause it to fracture, but these are engineering problems that we think are very solvable.
While some researchers are exploring new ways to combine materials, others, like David Mueller, are fascinated with a newly discovered treasure, the strongest material ever found, graphene. Made of pure carbon, graphene behaves a lot like a metal, but it's about 200 times stronger than steel and harder than diamonds, even though it's just 1 atom thick.
Graphene has incredible strength. Combined with incredible strength, it has incredible flexibility.
How strong is graphene? Some researchers estimate it would take an elephant balanced on a pencil to break through a sheet of graphene the thickness of saran wrap. Where can it be found? You have to bake it. First, take a piece of copper and place it in an oven. Fill it with a material that contains carbon. David Mueller uses methane, a gas that's a combination of carbon and hydrogen.
We knock all the hydrogen off it by heating it up very hot, so it gets turned into just carbon atoms that are floating around in a vapor. Those carbon atoms fall down and bombard a flat surface. So the way to think of this is my copper surface is just like a cold window on a cold day, and then little bits of moisture are in the air and they start to condense onto my cold window, and instead of growing little ice crystals that decorate all the way across my window, I'm going to grow little crystals of carbon that are going to decorate my copper surface. And eventually these little crystals are going to grow bigger and bigger and bigger until eventually they touch each other, and then I have one uniform continuous sheet of carbon, and that will be the graphene.
What makes this incredibly thin layer of carbon so strong? It all comes down to the arrangement of its atoms. When 6 carbon atoms bond, they form a hexagon. And as more and more carbon atoms join the group, more hexagons take shape.
So you can imagine that if another carbon atom comes down and lands over here, right in the middle, it's got nothing to stick to. It's going to keep rolling around, and then it gets to the edge of the sheet of the graphene and says, wait a minute, there's a dangling bond, I want to attach to that, and then it'll continue to grow out, and that's why the sheet gets bigger and bigger and bigger.
Once the baking is done, the graphene-coated copper is taken out of the oven and placed in a solution that slowly etches the metal away. What's left is a small sheet of graphene. Exactly what can you do with a single layer of graphene that's so thin it's barely visible?
So we could imagine graphene would be very valuable for things on the nanoscale.
Because it's both tiny and strong, it could fit inside a cell for medical applications, or be placed in dust for environmental monitoring. But graphene might also have applications on the megascale.
If you could build cables, for instance, for holding up suspension bridges, if you could get to that size scale, then that would open up incredible new engineering opportunities for creative people to make structures that we really can only dream of today.
Is graphene the next big thing? No one can predict if new metals like metal foam or graphene will live up to their promise. But there's no doubt that metals have revolutionized life on Earth. From the beauty of gold, to the smelting of copper, to the creation of bronze and steel, and in the future, materials we can only dream of.
And the astonishing thing is that the work of engineers, of metallurgists, and of chemists every year brings us new formulations, new possibilities that makes things lighter, stronger, stiffer, faster than anything that came before.
That the elements progressively take shape, bonding together in a process called fusion.
You can sort of imagine building up all the elements that exist in the universe by taking a pile of neutrons and protons and electrons and putting them together to build up bigger and bigger and bigger atoms.
When the number of protons and electrons hit 26, forming iron, the process stops.
Once iron's made in the core, that's it. There's no more available energy for fusion. Those massive stars will explode and go what's called supernova.
One of the key open questions, though, was what about the heavier elements? What about gold and platinum and uranium? Where do those come from?
At the end of supernova explosions, new kinds of stars are formed, called neutron stars. They often come in pairs, binary stars.
They're extremely dense and compact and heavy. It weighs about 1.5 times the mass of our sun, but it's the size of a city like New York or London or Boston. And they incorporate a lot of neutrons, which is why they're called neutron stars.
Some scientists theorize that elements heavier than iron were created in the collision of 2 neutron stars. What happens when they collide? Fusion on a massive scale. The elements were spread throughout the cosmos, so they were... Gold atoms love to be together, but when it comes to bonding with other elements, they're downright antisocial. When atoms bond, they do it through their outermost electrons, by sharing or swapping them. But gold's 79 protons fight the urge because they have an immense positive charge.
That positive charge pulls in the electrons. The real consequence is that the outermost electrons of gold are much less available for doing chemistry than we might otherwise expect.
That's why gold doesn't bond with elements like oxygen that cause metals to tarnish and rust.
The reason that we're able to appreciate the gold masterpieces from 2400 BC is because gold lasts forever. It is just as beautiful today as it was thousands of years ago. You can't say that about anything else that you could work in.
How did such a unique metal form?
It's not easy to make an element. You need temperatures that are extreme, and we're talking millions of degrees. The heavier the element, the hotter the temperatures required to make it. And you find those temperatures in the cores of stars that are 10 times the mass of the sun or greater.
It's within the intense heat and pressure of these massive cores.
I just want it. Can you see myself? Can you see myself? Can you see myself?
By the light of an ancient campfire, a discovery was made that changed the course of history.
We don't know exactly how it happened, but I sometimes wonder whether it wasn't a complete accident.
Whether by chance or through sheer determination, once humankind learned how to harness the power of fire, we left the Stone Age behind, forging our way into the modern world with copper, bronze, iron, and steel, the metals.
A world without metals would not have tall buildings, it would not have fast vehicles, it wouldn't be able to have electricity. Really, our entire modern world is built on the backbone of metals.
Our journey begins with a metal that's transformed life on Earth through its beauty. A metal that fortune hunters were willing to die for. And not just in the movies.
There's nothing more beautiful than gold. Nothing in the world. You just feel it when you see it. Ancient people valued gold before the concept of currency or money even existed. It's something that people intrinsically knew had worth. Gold is absolutely magical. Gold is the most fantastic jewelry metal to work with. It's so soft. It's so flexible. It's like butter. Working with gold ruins you for any other metal. You're never the same again.
Jeanette, a master jeweler, is making a pair of gold earrings.
I specialize in ancient jewelry making techniques. The kind of expertise and skill that were used for making jewelry really made it an art form. I'd make my own wire and sheet and practice techniques like granulation. The technique I'm going to use for the hanging fringe actually originates from Troy from about 2450 BC.
Gold is unique among the elements. Gold is extremely resistant to oxidation, to rusting. If you make an object out of gold, it's the one thing that you have that doesn't degrade. So to ancient people, it must have been very, very appealing.
The color of gold draws you in. Ancient people saw it and knew that it was something incredibly special.
Gold is not only beautiful, it's rare. In fact, if you take all the gold that's been mined to date, it's estimated it would fill about a third of the Washington Monument. But to understand what makes this rare and noble metal last forever, we need to take a closer look. A much, much closer look. Using one of the most powerful electron microscopes in the world, David Mueller studies the elements.
Probably the most fun in the lab is when you put something in and the picture comes up and you look and you go, well, that's not what I expected. That's interesting, and that's usually the start of a new scientific discovery.
Today, Mueller is observing the curious behavior of gold, atom by atom. All elements are made of atoms. Inside, is a nucleus filled with positively charged protons along with neutrons that have no charge at all. Swirling around the nucleus in a cloud are negatively charged electrons. It's the relationship between gold's nucleus and its electrons that holds the key to its resilience.
We're now at 7,000 times magnification, 7 times higher than the highest magnification of an optical microscope. And if we zoom up some more, you can start to see there's this nice pattern. These are little islands of gold. And if we zoom up a little bit further on them, you'll start to see little bright spots all by themselves. Those are individual atoms.
Every one of these clusters contains thousands of bright dots, thousands of gold atoms.
Little gold atoms form small clusters, and they keep rearranging and changing. They're not static, they're not stable, they're dynamic, they're moving all the time.